All right, well, given that everybody has calmed down, it is a great honour and a great pleasure to welcome everybody here to what, by my count, is the 39th CEDAR, annual CEDAR workshop. Although I should say there's always been some uncertainty about actually when we started counting. So as a scientist, I probably should say this is the 39 plus or minus 1 CEDAR workshop. And, you know, maybe we had a semi-workshop in 2020 and 21, so maybe it's even a non-integer, 39 point something plus or minus 1 point something CEDAR workshop. I'm delighted that everyone's here. I can see lots of old friends and lots of new faces. This is an annual tradition for many of us. For others, it's their first time here. It's very exciting. When we were choosing the venue, one of the things we were asked to do is make sure we didn't find somewhere that was swelteringly hot. I think we've achieved that. So I'm looking forward to a really fun workshop. Before we get started, I need to thank a lot of people. There's been a huge amount of work to get us here. Members of the CEDAR Science Steering Committee, our fantastic student reps who organised a really tremendous day yesterday, and I think we'll hear from them shortly. Our DEI task force has been very active, working on DEI things, and I'll say a little bit about that in a minute. Our supporters at CPAS, conference organisers, Michelle, Maggie, Liang, Jessica, if you've got any problems, they're out there, they can help you, and they've really done a great job getting this workshop together. NSF, of course, sponsoring it, and I do want to thank everybody who signed the community statement, who signed the community statement from CEDAR regarding the GDC mission. We'll hear more about that later in this week, and I think that was a good thing. But most of all, I actually want to thank everyone here. It's you people who have come here. You'll be making the presentations. You're the conference, and thank you for attending. This is, as I said, this is our annual meeting, and you're the ones that will make it a success. So thank you. Let's see. I've only got a short time up here, so I wrote down on a piece of paper everything I thought you'd want me to talk about. So. As I said, the CEDAR Science Steering Committee has been busy. I've got a few announcements to make, or items of news to announce. Some of the things that the Steering Committee has been working on in the last year. Finally, after nearly 40 years, we actually have a set of bylaws, and Angeline will be talking about that later this morning. It might sound a little bit pedestrian, maybe not the most exciting thing, but it turns out, for a mature science body like this, we actually do need to have that. So, and it has been very helpful to us just organising this meeting. So, I'm pleased that we finally, after all this time, have codified our bylaws. So that's good. Another thing I need to mention is that we now have a CEDAR Code of Conduct. It's posted outside on poster boards out there. We are required to have that by NSF. I'd like everyone to read it. I think it's up on the screen there. Let's see. It's quite long, 3 pages. We'll say a little bit more about that after the break this morning. But this is important. As a community of scientists, we do need to have a strict set of guidelines as to what's acceptable and what's not acceptable. So please read the Code of Conduct. It's posted outside the workshop there. The most important take-home from that is if you see something going on at the conference, or if you're aware of something that someone is doing, please report it to one of the CEDAR Science Steering Committee members or conference organisers, so we can take action if necessary. So that's very important. Another thing that has been active in the last year, as I said, is the DEI task force. They've organised a number of events here at this meeting this week, and they've been involved in a lot of activities. And, if I asked this audience, why do we have CEDAR? Why do we bother coming to flying everybody to a venue? A lot of people would say, well, we come for the science. But really, you can do most of the science remotely these days. The reason we get together is to be a community of scientists and to interact and to be welcoming and inclusive. And that's really what DEI is about. It's like breathing. If it's working properly, you wouldn't notice it. Everyone would just be working together. It's only when we're not doing it right that things go seriously wrong. So this week, be welcoming, be inclusive, don't be aggressive if you're looking at a poster and there's something that you feel could be done better. Do that in a positive way. Don't be aggressive there. And as I said, just be welcoming. And be grateful for the fact that people have come here and presented their work. Something that I'm very excited to announce is that CEDAR and GEM are working together now to, I can't say we've got this fully organised, but we're working to have a joint CEDAR-GEM meeting next year in 2025. We don't have a venue selected yet. I'm really delighted to hear the positive response there. We asked GEM whether they would like to do it, and they came back to us, and I think they're pedal to the metal enthusiastic as well. So the plan is for it to be a parallel workshop, so we're not going to do one week followed by another. It will be the 2 workshops running in parallel with joint sessions. So as I said, we're working on that. We don't have a venue yet, but CPAS has been looking for venues for us, and I just found out yesterday that they've got about half a dozen options that we can look at. So it will be probably a larger convention centre given the size of the joint meeting, but that's something that we're working on right now. So hopefully, as I said, we don't have a venue secured. We can't say for sure that that's going to happen, but it's in the works. So hopefully we'll have some good news on that shortly. And then the final thing in terms of announcements, well, actually, I guess a couple more things. Shortly after this meeting sometime, the new decadal survey will come out, and so we have decided that once that happens, the CEDAR Science Steering Committee should begin a process of developing the next revision of the CEDAR strategic plan. Christina Lynch will be saying a little bit about that later in the week, and I think until the decadal survey comes out and possibly NSF has a chance to look at it and maybe thinks about portfolio reviews and what have you, we can't be too specific about what a new CEDAR strategic plan will contain, but what we want to do is start the process. It takes several years of discussion and presentations at workshops and things to develop a proper, inclusive, community-driven strategic plan. So we have to wait for the decadal survey to come out, but we want to start the process as soon as we can after that, and I think Christina will be talking about that later this week. The banquet this week, we have the after-dinner speakers at the banquet will be provided by our student reps again, same as we did last year. We had Vincent last year. This year we're going to have several student reps, and they're going to be talking about just their experiences doing field work for CEDAR, and so I think that will be fun. And our students are doing all sorts of really exciting stuff. One of the great things about working on a scientific discipline like CEDAR is the opportunities you get to go into the field or to work with state-of-the-art computers or state-of-the-art instrumentation. And so having our students giving some presentations about their experience doing CEDAR science, I think will be a good after-dinner, a good way to do the after-dinner banquet speech. So enjoy the week, reach out to your collaborators, look for new ideas, talk to program directors, enjoy the activities, enjoy the venue here, it's going to be great. So I think that's all I have to say in the way of welcoming comments. And I think next up we have the student report. So actually, there is one other thing I wanted to say, and that is, sorry, just hold that thought. I wanted to comment on the one of the traditions we have that we've done every year for at least as long as I've been here is to have the students introduce all these students who are participating here. And I wanted to comment on just how important I think that is. When the students stand up and look around the room, in what will just seem like a blink of an eye, those students who are standing up will be the new CEDAR Science Steering Committee chairs, they'll be program directors, they'll be proposing space missions. Those are the people that are going to be leading our field in. It might seem like a little way off if you're a student, but trust me, you'll wake up one day and find yourself in charge of a space mission or something. It just happens so fast. And so, these are the people that really, meeting it's really important, the student contribution and the way we interact with them. So I think that's a very important part of our meeting. It's a great tradition. I'm looking forward to it. So over to you guys.
All right, thank you, Mark. Yeah, for those of you who don't know, Andrew Pepper is the outgoing student rep, and I'm Sophie Phillips, the incoming student rep. And so as part of my responsibilities, we've been working hard to plan student days for the past year, and that happened yesterday. So I'm excited to give the report on how that went. Spoiler alert, it went well. So I'll just take you through the agenda of the items that we went through yesterday. We started off the morning with a series of lightning talks, and they were seriously amazing. If you weren't able to make it, the recordings will be on YouTube, and it was really informative and incredible, so thank you to all those speakers. And then we got a talk from NSF about grants and proposals, best practices for proposal writings, specifically for graduate students. And then we heard from Caitlin Greer about grand challenges at CEDAR. What are they and how can students get involved both this year and in the future? Then after our lunch break, we had another exciting talk from about science communication and networking from Rachel Lenz of the GDC mission. And then after that, we had a sort of split choose your own path where we had the Thai GCM model demo going on in the East Coast room, and then we had a career panel going on in this room, and so that was really great too. And then after that, we finally had a bystander training and what we can do as graduate students at our own institutions and at CEDAR itself. And that was a really great DEI session. There were really great conversations that were had. So if you came to that, thank you so much for providing really thoughtful insight. And then after that, we did a little outdoor activity, which we have pictured here. There was another picture, but I don't think it made it onto the slide. There was a picture of the model demo, which is really fun too. But yeah, we want to give a huge thank you to everyone that made this day happen, to the speakers who volunteered your time to make such informative presentations. Thank you, it wouldn't happen without you. Our student committee, this was our first year having a volunteer student committee, help us both with student day execution and with student events that are going to happen throughout the week. And we couldn't do as much as we can do without them. CSSC, thank you for all your guidance. NSF and CPAS, again, we wouldn't be here without them, so a huge thank you to them. And then I just have two more announcements in regards to student-related things. First, sadly, Andrew Pepper is going to be leaving us. He's the outgoing student rep. So if you're interested in being student rep, feel free to email me or Andrew. We're going to make those decisions later on this week. And then secondly, you may have already seen, but outside on the registration table, there are little sheets for a scavenger hunt, a student scientist scavenger hunt. So there'll be a list of 10 items. You have to go and find like 10 people that fit those descriptions. And at the end of the week, if you finish that, you'll be put into a raffle to win a really cool Lego set. So we've been working with Caitlin Greer on that, and so that's really exciting. So feel free to participate in that as well. And then I think on that note, we're going to do the institution reading, so I'll hand it off to Andrew.
Thank you, Sophie. Good morning, everyone. As Mark alluded to, don't need that pen anyway. As Mark alluded to, we're going to be reading through the list of institutions that send students to CEDAR. So we're going to start with, of course, close to home, Clemson University. You guys got to stand. Thank you. Okay. Case Western Reserve University. Oregon State University. Illinois Institute of Technology. National Space Science Center, Chinese Academy of Sciences. University of California, Berkeley. Utah State University. The University of Texas at Dallas. Prairie View A&M University. Dartmouth College. National Institute for Space Research, INPE. Hikamarka Radio Observatory. Virginia Polytechnic Institute and State University. University of Colorado Boulder. University of Michigan at Ann Arbor. New Jersey Institute of Technology. Thank you, Lindsay. Embry-Riddle Aeronautical University. Pennsylvania State University. Nice. Okay. And Stanford University. Nice. Okay. And then Sophie and I like to divvy this up, so that's it for me.
Oh, no, I'm doing
wait,
second half.
You get a second half.
We just thought it'd be faster than going back and forth.
Yeah.
Don't worry. You can yell at me later if I still forget some. All right, picking up with Virginia Tech. Space Weather Division, National Institute for Space Research, Brazil. University of California, Los Angeles. Dartmouth College. National University of Engineering. Arizona State University. University of Alaska Fairbanks. University of Science and Technology. Pontifical Catholic University of Peru. Royal Melbourne Institute of Technology. Auburn University. University of Texas, San Antonio. Institute for Space, Earth, Environmental Research, Nagoya University. University of New Hampshire. Korea Polar Research Institute. The University of Scranton. Scranton. Boston University. University of Texas, Arlington. Korea Astronomy and Space Science Institute. Cornell University. And finally, University of Maryland. Great, thank you so much for, which one did we miss? United States Military Academy. Great. Hopefully we got them all. But thank you so much for standing, and it's really great to see all the schools that are represented by the students, so thank you so much.
Then go to break. And then I think we're going to welcome Mark back up to the stage to continue on. Thank you, everyone.
Yeah, thanks, guys. That was great. And I was thinking as everyone was standing up there, I don't know, but I would guess maybe 2/3 of the room here have stood up at some point in their career for the student introductions. So, you know, we've been doing this for as long as I've been coming to CEDAR, which is about 30 years now. So, as I said, I think it's a great tradition, and many of our leaders here now have been in that student group in the past. All right, so the next item on the agenda, it's my pleasure and honour to welcome Tai-Yin Huang from NSF to give us some opening remarks. NSF are our agency sponsors for CEDAR and for a lot of the work we do, and I'm looking forward to Tai-Yin's welcoming remarks from NSF. Thank you.
Okay, good morning. Before I start, I would like to say that I did not I did not discuss with Mark, what I'm going to say, but you're going to hear, there's a lot of common things, from my speech, and this is my note, a little bit, larger than Mark's. So before I start, I'd like to. I'm Tai-Yin Huang. I'm a program director for the data infrastructure program, and also I'm also help manage the Around Me program. So Shika Rosetta, she's the program director for the Around Me, but unfortunately she could not participate in today's CEDAR meeting because she had her injury, so unfortunately she has to cancel her trip. She was very much looking forward to it. But anyway, so before I start, I really like to thank the CPAS and also the steering committee for putting this to work, because there's a lot of behind the scenes things that has to be done in order to run a workshop successful. So thank you so much, and for whoever that's involved in this preparation for this workshop. And I was looking at the CEDAR website to kind of trying to find out the histories of CEDAR workshop, and I noticed that the first one was actually organized, was held in 19, I'm sorry. In 1986, and it was actually at the NCAR, the facility, So it's almost like 40 years. I think next year maybe we're going to see the 40 years, or like Mark said, either it's next year or 2026. That will be the fourth year's anniversary of the CEDAR workshop. And just so you know, CEDAR, GEM, and SHINE, all the three community workshops, they are, the signatures or the flagship, let's say this way, the flagship of NSF-sponsored workshop. We're very proud of it, and we try to support it as much as we can, and we also like to, see students, we would like to provide funding to for student travel so that we can enable the students, more students to come to this workshop. I know that when I was a grad student, this is one of the things during the summer that my advisor would send me to CEDAR, primarily because NSF, providing the travel support. And we like to hope, we hope to continue this tradition, because this is a very, very close community, and we like people to come together to exchange ideas, to share their ideas, and you're going to find that, the students, you're going to find a lot of things to learn from. I know I was overwhelmed when I was a grad student, but thankfully, all these people, they're giving their tutorials, they're giving their plenary talks, they provide a lot of wisdom to the community and to students who wants to stay in this this community. So definitely make the best of your time here. I know it's overwhelming. I look at the agenda, it's just like I want to go to every one of them, but there are quite a few parallel sessions. So so do your best and then learn as much as you can. And in the meantime, go talk to people, because this is also a place that people communicate with each other, share ideas. Sometimes the bold ideas or the great ideas or the collaboration come that is a result of the discussion and networking. So so I think that is about it. Oh yes. Another thing, and again, Mark, talking about DEI effort and also code of conduct, we are part of this community. Everyone can play a role in creating the environment that you would like to be in. So, everyone wants to be in an environment that's, that is welcoming, that is respectful, and also that is safe as well. So do your best, to be a good citizen and maintain this, good rapport with your peers, and have a positivity to this, to this community. So with that, let me see. Make the best of your time. Yes, to PI. Okay, yeah. So Roman and I, we're all here. So if you have any questions about proposals and NSF, just contact to us. If you don't know us, make your, just introduce yourself. Don't be shy. We're here to answer questions. And also, if you want to be, and for those who are established in this field, if you want to be a panelist or if you want to be a reviewer, just come, contact to us. We love it. And with that, I think that is it. Yes, yeah. Okay, great, thank you. Enjoy it.
Thank you, Tyene. And we very much appreciate all the support that we get from NSF, and just the fact that we've been able to have this workshop and run CEDAR. It's astonishing to me to think that CEDAR is about to turn 40. Well, I guess if you went from 1886, it would be 140. But so I think the next item on the agenda is something that we do every year, and it's something that's a great pleasure for me to introduce, and I think everybody here should feel good about it. And this is to conduct our what we call CEDAR Prize Lecture. So it's a lecture that we we invite a speaker every year to give in recognition of a really significant piece of work in the last, I think, roughly 4 years. Maybe it's a little bit plus or minus, but the last roughly 4 years. So we have several awards. We have a distinguished lecture, which is awarded for a longer body of work, and we will be hearing a distinguished lecture later this week. But the prize lecture is meant to be something that's impactful and recent. And so the way that we do this is we call for nominations from the community for people to suggest who might become the prize lecturer each year. We discuss those nominations within the CEDAR Science Steering Committee, and based on that, we select a speaker. And so it's my great pleasure now to announce that the speaker for this year's conference is John Emmett from Naval Research Lab, and he will be talking about the development of the MSIS 2.0 and 2.1 models. And I was thinking to myself, if some passing senator or other disinterested person came by and wanted to know why we chose this particular topic as our prize topic, why this is so significant, I was thinking to myself, it feels to me a little bit like we're awarding a prize to the person who invented duct tape, or actually to the group that invented duct tape. It's one of those things that just works, and you need it, and it has to be there. And so that's what MSIS is for us. It's just a tool that is the thing that holds our community together in some ways, just like duct tape. When the astronauts coming back from the Artemis 1 mission are about to re-enter the atmosphere of the Earth and they're looking down, that's going to be a stressful time, and they'll probably have a checklist of the things they need to go through. And I think the first thing on that checklist will probably be, before we re-enter the atmosphere, make sure everybody knows where the duct tape is. And the second thing they'll say is, have we got the latest MSIS run so that we've got our re-entry trajectory organised correctly? So, this is something that's important. So I think Fabrizio Sassi will, is Fabrizio here? Yep. Was the person who submitted the nomination for John, and I will invite him to give a better introduction than I just did. What can I say after you? So I will hand it over to Fabrizio, but I'm very much looking forward to hearing John's presentation on MSIS. And I should say, one we recognise, and John recognises, that MSIS is not just his work, it's the work of a lot of people, and I think John will make that clear. So thank you.
Yeah, I'm not sure what to say after the duct tape thing. This CEDAR Prize lecture is, as Mark was saying, is to recognize the work that John Emmert and his group have done for the series of models like NRL MSys 2.0 and 2.1. Everybody in the community is using these models in one form or another. I've used these models for my modeling work when I was extending the anchor modeling to the thermosphere. I couldn't have done that without MSys. I've known John professionally and personally for a long time, or at least since my tenure at NRL, at the Naval Research Laboratory in DC. And I've known him professionally and personally, and I think he's a great person, a great guy, and a great scientist. And for the last, I think, 7 or 8 months of my tenure there, you were also my supervisor, so something like that. So he's a good supervisor. As I said, this nomination, this prize follows many years of work that John and his group have done in support of the CEDAR and heliophysics communities. This is, the duct tape analogy is very fitting. And really this has tied together the community, and especially in these times of difficulties in getting things done, reducing funding in different forms and venues. And in particular with the upcoming design of and implementation of flagship missions at NASA, the involvement of CEDAR community in understanding, interpreting, and assisting space flight missions with ancillary modeling work, the importance of NRL MSys suite of models cannot be understated. They really, in my opinion, represent a true symbiosis between NASA supported space community and the network of ground-based observatories that is supported instead by NSF, covering what we have come to know as the SARE, the Space Atmosphere Interaction Region. So again, this award goes to John, goes to the NRL MSys models, it goes to the people, the entire community that has worked with John in putting up these 2 models. So John.
Okay, well, thank you for the kind introductions by Mark and Fabrizio, and I suspect that Fabrizio is feeling a little guilty for defecting from NRL to NASA, and so, but I appreciate the outcome. I'd also like to thank the steering committee for selecting our work for this great honor, and my co-authors and I are very grateful for the recognition. And as Mark and Fabrizio said, this really truly is both a team and community effort to put these models together. I've listed my co-authors here along with the data providers that we've collaborated with directly over the years. But equally important are the many, many more people who design, build, deploy, and operate instruments and measurement retrieval techniques that make this kind of work possible, and especially collecting these data over several decades, is really important to this kind of work. So for my presentation, I'd like to just begin with a brief overview of MSys, what MSys is and how it functions, and then I'd like to give a perspective on the importance of this kind of work, empirical models, to advancing science itself. And I'll do that by showing some examples from history. Then I'll give a history of MSys itself briefly, and then dive deeply into the MSys 2.0 and 2.1 versions that we released in the last couple of years. And I'll conclude by sort of giving an overview of what we're currently working on and our visions for the model's future, and then finally discuss a little bit about the role that empirical models play in both geospace and science and aeronomy. Okay, where's the advance here? Is it this? How do I advance the slides? Ah, there it is. Sorry. Yep, you help me out here, Mark? Oh, there it is. Sorry, I'm looking in the wrong. I'm using the laser pointer. Got it. Okay. Okay, sorry about that. EMSIS describes the average behavior of the observed atmosphere as a function of the three-dimensional location, the cyclical time variables, day of year, universal time, and local time, and the solar and geomagnetic activity drivers. And now the number of densities that it outputs include all of the species that contribute significantly to mass in one area of the atmosphere or another, as well as minor species like nitric oxide, and also most recently, minor species like atomic nitrogen, and also most recently the addition of nitric oxide. It also has what we call a anomalous oxygen component, which nominally describes a population of hot atomic oxygen that contributes to satellite drag, as well as the contribution of O+ ions to satellite drag. And the model also outputs mass density, which is derived just simply by summing the contribution of each species to the total mass. Now, EMSIS is based on data, so it is an empirical model. But it's perhaps best categorized as a semi-empirical because it does include important physical constraints, which I'll talk about in more detail later. EMSIS is appropriately called a climatology because it does describe the average observed state. However, it nonetheless does represent accurately short-term variations in the atmosphere as a result of the strong and predictable forcing from the sun and geomagnetic activity, and also persistent variations that are harmonics of one day. It's a parametric model because it uses a analytic mathematical formulation whose parameters can be tuned. And these kind of models used to be called static, and this is because the Okay, these models also used to be called static because the model parameter values are fixed in time except between model revisions. However, given enough data, there's no reason the model parameters couldn't be tuned on a day-to-day basis, and that is actually an application model that we're currently exploring. Okay, so before I take a deeper dive into EMSIS, I'd like to give my perspective on the contribution that empirical model makes to fundamental science. And here I'm going to push back on Mark's analogy. Yes, EMSIS is very good duct tape. And by the way, duct tape itself isn't that good. I don't know if you've ever tried it for duct tape, but yes, EMSIS is a very good tool, but it also, the act of putting these models together really does constitute fundamental science. And so to illustrate this, I've taken an example from science history. And so suppose you have this set of observations here with the attendant uncertainties, and you wish to characterize their behavior in order to predict what future observations might do. Now, at this point, I'll make a disclaimer and state that these are synthetic values that I'm showing here. These are not actual real historical observations, but the illustration is actually numerically based on a real historical example. So after much analysis and futzing around and some underlying hypotheses, you come up with this fit of the data, shown by the red curve there. And now you see this parameterization that I use here, this formulation. You might say that, well, that's a bit overly complex for this fairly simple curve, but it also might give you a clue as to where this example is coming from. So you look at this fit and you notice that, yeah, it's representing the data to within the uncertainty, and so you rightly conclude that this is the best you can do, and you declare victory. However, at a later date, somebody else comes along and makes even more precise measurements, and now you can see that there are now significant differences between these new data and your original model. And so the first thing you try to resolve these discrepancies is to retune your model to the new data, but that doesn't change the model much, and you still have these disagreements between the new data and the model. So clearly, a revision to the formulation is needed, to your theory, basically. And so after more experimentation, you come up with a new revised and better formulation to better capture what you see in the data here, as shown in the Grieve curve. And so looking at just that fit now with the data, you conclude again that, yes, we've represented the data to within the uncertainty, and so we declare victory again, at least until even more precise measurements become available. But even when that happens, this model still will be a very useful benchmark for assessing those new observations. So you may have already guessed where this example is coming from, but if not, this is the Kepler's laws of planetary motion. And the data are the right ascension of Mars as viewed from Earth during a period of retrograde motion. The original model is the Copernican theory of circular orbital motion centered around the sun. Now, in this case, I've actually neglected epicycles, which even though Copernicus revised the Ptolemaic theory of orbits and got rid of the biggest epicycle, he did not abandon them altogether. I should also point out that in my synthetic data, I cheated a little bit and I assumed a perfectly circular orbit for Earth in order to simplify the calculations. Now, the new data is illustrative of the highly precise observations that the Danish astronomer Tycho Brahe produced, which Kepler used in generating his elliptical orbits. And now, Kepler's analysis was, of course, primarily geometric because he didn't have the mathematical tools to parameterize and tune his model the way we would today. But it nonetheless constitutes an empirical model of the data that he had. And of course, it contributed to the development of Newton's theory of universal gravitation, of which the Keplerian orbits are the exact solution to the two-body case of that theory. And in fact, even to this day, the Keplerian orbits are still widely used in astrodynamics as a baseline for predicting positions of satellites and planets and things like that. So, not just duct tape. So, Kepler's laws are not the only empirical model from history that contributed to science. Here's a short list of some others. All of these models or laws were originally based either partly or entirely on data. And one interesting case, oops, I lost my equation there, sorry. Forgot to put the image in there. The Planck's law is an interesting case because this is the law that describes the spectral density of radiation emitted by a black body. Planck originally constructed that from observations, but subsequently derived the same form from physical considerations. Now, of course, you can see that most of these laws are simple laws of proportionality, whereas for models of the environment, like the atmosphere, your empirical model is going to necessarily be more complex because the system is more complex. So, therefore, it might be useful to specially define an environmental empirical model as a description of the average observed behavior of the system state variables with appropriate physical constraints. Now, you might also argue whether it's not as necessary for that model to be a parametric model. You can discard that requirement, and then that would broaden the definition to include, say, machine learning models. But one advantage of parametric models is that they can be used to attribute variations you see in the data to individual factors. Okay, so turning now to the history of IMSIS itself. IMSIS is now about 47 years old. It was originally created at NASA Goddard by Alan Hedin, and it was the acronym MSIS derives from the mass spectrometer and incoherent scatter radar observations that the model was originally based on. The model originally represented the upper thermosphere only. But in 1983, it was extended down to the lower thermosphere using new measurements as well. And then in the IMSIS 86 version, assimilated new measurements from the Dynamics Explorer 2 satellite into an expanded formulation. And in 1990, Alan extended the model to the ground using sounding rocket data and tabulated middle atmospheric temperatures. And this formed the basis of EMSIS E90, where the E signifies the downward extension. In 1995, Alan Hedin retired from NASA, and at that point, Mike Piccone and Bob Meyer at NRL invited him to come over and transfer custody of the model to NRL so that NRL could continue development. And that eventually culminated in the release of EMSIS E00, which added mass density data from satellite drag, O2 data from soil occultations, and that was when this new anomalous oxygen species was added as well. Around 2013, we took the model up again, and you can see it took a long time to get there, but we culminated in the development and release of EMSIS 2.0, and then also EMSIS 2.1, which added nitric oxide, and that is going to be the main focus of my talk today. I've listed the citations for those two papers here in the bottom right, and I'll also note that the Fortran code to run the model is included in the supporting information of those papers. Okay, so let's start going into some more details. So this chart shows the data that went into the EMSIS E00 model. So as I said, the original model was based on mass spectrometer data, which basically covers altitudes from 100 kilometers to 600 kilometers approximately, and also incoherent scatter radar measurements of exospheric and lower thermospheric temperatures. Also used, as I said, was satellite drag data of mass density, and then the solar occultation data for O2, and then the lower atmosphere using the sounding rocket data and the tabular information on the lower atmospheric climatology. So one of the things we had the advantage of when starting EMSIS with the EMSIS 2.0 development, there became a wealth of new data available in the middle and lower atmosphere. And so we took advantage of this, which, this includes occultation data, passive remote sensing in the microwave and infrared regions, as well as ground-based LiDAR observations of temperatures. And we also used numerical weather prediction reanalysis data, which, with like MERA and the NCEP data sets, which, span many years now back to the 1970s. So because of this wealth of new data and because that was the oldest part of the model, our development focused mainly on the middle and lower atmosphere for EMSIS 2.0. However, we did make some changes to the thermosphere. Namely, we retuned the atomic oxygen to better match orbit-derived observations of the mass density in the thermosphere. But otherwise, we largely retained the EMSIS E0 thermosphere, and that's actually something we want to work on next, is to start looking at that part of the atmosphere. Okay, so now I want to talk a little bit about the formulation of the model, and one of the main constraints that we look at in our development is the relationship between temperature and density, because the model does represent both those features. And of course, density is strongly coupled to temperature via hydrostatic balance and also the ideal gas law, which are shown here. And so if you solve these two equations for mass density, you get the following equation, which expresses the log of the mass density as a function of the log of a reference density, plus the relative changes in temperature and the mean molecular mass. This expresses the ideal gas law. Plus another integral term that also involves the mean molecular mass and the temperature. Now, this integral term is key and actually usually ends up dominating, especially in the thermosphere, dominates this equation. And this represents the expansion and contraction of the atmosphere as you have heating and cooling. And so I'm showing an animation here that shows an example of the response of the thermosphere to increases and decreases in the EUV radiance from the sun. The EUV radiance derives increases in temperature in the thermosphere. And then that, in turn, via this hydrostatic term, causes the entire thermospheric column to expand so that a level of constant density raises in altitude, and you get increases in density. And this is actually the main mechanism by which space weather affects satellite drag. So there are two limiting, simpler cases of this equation. In the upper thermosphere, things are diffusively separated so that each species follows approximately its own individual hydrostatic equilibrium profile with its own constant species mass. And so in this case, the equation simplifies then the hydrostatic term is just then now in the integrand, you just have the reciprocal of the temperature. The other limiting case is in the lower atmosphere, where the atmosphere is approximately fully mixed. And in that case, the mean molecular mass is approximately constant, and you get a very similar looking equation, except that now all the species collectively follow one scale height that's determined by this constant mean molecular mass and by the temperature. So the challenge then in trying to put together a whole model that covers all altitudes is to seamlessly represent this transition from the fully mixed atmosphere to the diffusively separated atmosphere. And this transition takes place approximately between 100 and 200 kilometers. So the solution we came up with is to define an effective mass profile that monotonically shifts from the lower atmospheric mean mass to the individual species mass in the upper thermosphere. And I'm showing here the effective mass profile that we're using for molecular nitrogen, which makes a short jump from 29 atomic mass units down to its own species mass of 28. And this is constructed as a piecewise linear function that is constructed around a hyperbolic tangent function with different scale heights on the upper side and the lower side. So that this profile, other than the two limiting masses, this profile is defined by just three parameters: the transition height, which could also be viewed as the turbopause height, and then the upper and lower scale heights. And so using this parametric profile, we come up with this generic species density profile formulation that we used in EMSIS. So again, we have a reference density. We have the hydrostatic term and the ideal gas law terms. For some species, like atomic oxygen, we have an additional correction term that accounts for chemical loss on the bottom side of the peak. The atomic oxygen kind of goes away as you go down in altitude. And we have a second term that kind of that accounts for, it's kind of an ad hoc way of correcting for dynamical effects in the thermosphere in the transition region that are not amenable to a simple effective mass profile. And so one example is the diffusion of O2 and N2 with respect to O, and also the photodissociation of O2. So an important and intended consequence of this formulation is that it couples the density to the temperature throughout the entire column. And this means that if you perturb the temperature parameters in the lower part of the model, it will affect density at all higher altitudes. And so in this sense, this is part of the reason why we sort of refer to this as a whole atmosphere empirical model. Now, this is a major departure from the previous approach used in EMSIS E00 and earlier models, which separately calculated a fully mixed profile and a diffusive profile, and then did average them together in the transition region. Now, of course, this formulation relies heavily on the temperature, of course, because it's coupled. So I'll also just very briefly review what the temperature parameterization looks like. So above 122 kilometers, we use the Bates profile, which goes back to 1959. And this is basically an exponential relaxation that relaxes to the exospheric temperature. It's described by just three parameters. And at lower altitudes, where you don't have such a monotonic dependence of temperature, we use a cubic B-spline basis. And both of these can be expressed in the reciprocal of temperature. And part of the motivation for this selection of the parameterization is that it's can be integrated in closed form. So the 1 over T formulation can be integrated in closed form, and also the piecewise effective mass can be integrated in closed form, so that when we're having to calculate the hydrostatic term with the mass and the temperature in the model, we can do that by parts and still have a very robust calculation of the integral. Okay, so I won't go into the detail on these other changes to the formulation, except for one. I wanted to point out that we did make some changes in the thermosphere to the intra-annual oscillation and atomic oxygen. And the motivation for this is that the upper thermospheric mass density shows a very strong and persistent semi-annual variation, as well as an annual variation. That was first discovered back at the dawn of the space age in the 1950s. It was also fairly recently discovered that the amplitude of this variation is larger at solar maximum than it is at solar minimum. However, EMSIS E00 goes in the other direction. It has actually larger relative variation at solar minimum, and that's a consequence of it being partly a temperature effect, where the cooler solar minimum background, you have smaller scale heights that sort of amplify the variation. So this is something we definitely wanted to correct in the new model, and so we added these new terms. And so here I'm showing the results here in the form of, we did this successfully in the form of residuals between models and data. So what's shown here are model minus data residuals with respect to orbit-derived mass density at 400 kilometers. And we do this kind of analysis just frequently to validate and verify that the model is doing what we want it to do. And so the goal for this is to have a flat profile of residuals. So in the top panel, I'm showing results for solar minimum, and the bottom panel for solar maximum. The red curves show the results using EMSIS E00, and the green ones are EMSIS 2.0. And you can see that the results for EMSIS E00 show a very large residual seasonal variation, which we don't want, and that this seasonal variation is different between solar minimum and solar maximum, which reflects the fact that the model is actually getting the opposite modulation of this effect that we want. But in the new model with these extra terms and with the new data, we've corrected that, and you can see that things are approximately, or at least much better, represented. You can also see an overall reduction in density that we deliberately put in the model, and this is due to a downward revision of orbit-derived mass density in recent years, but also tuning to a later epoch. The thermosphere is actually cooling and contracting in response to climate change, and this is resulting in lower densities over the years, and I'll talk a little bit more about that later. Okay, so now let's take a look at the statistical performance of EMSIS 2.0, and here I'm focusing again on the middle and lower atmospheric temperatures. So this table shows the residual standard deviation of the temperature observations with respect to the old model, EMSIS E00, in the left of each column, and EMSIS 2.0 in the right. And I've sorted the data into 4 broad altitude bands from 0 to 100 kilometers. And I've also highlighted in green the model that has the better result, the lower standard deviation of the residuals. And you can see that in almost all cases, the EMSIS 2.0 model is outperforming the old model, which is not surprising because we're using the new data. But I will point out here that when we did this validation, we used a different random draw of the data than we used to do the actual fitting. So this is, in some sense, a little bit independent validation of the model. And then again, we can do this residual verification approach and here I'm showing the average residuals for each data set as a function of altitude and bins. At the top panels, I'm showing results from 40 to 100 kilometers, and then on the bottom panels, I'm focusing in more on the 0 to 60 height range and focusing on a larger scale of temperature changes. So you can see that on the left, with EMSIS E00, we have fairly large deviations on average from the model, and most importantly, these deviations are highly consistent from data set to data set. So we know that there's a real discrepancy in the model. that we need to fix. And we did indeed do so in IMSIS 2.0. You can see that now the average residuals line up much more closely and, again, are in very good agreement with each other. So this is a very robust recalibration of the IMSIS temperatures. Okay, next I'll go on to another science highlight from IMSIS 2.0, and this deals with the seasonal dependence of mesospheric atomic oxygen and atomic hydrogen. Now, it was found in IMSIS E00 did not agree very well with the, in fact, it was opposite dependence, and the mid-latitudes, the seasonal dependence was reversed from what was being observed by atomic oxygen measurements from the OSIRIS instrument, which is a passive infrared sensor. And so, okay, well, we got to fix that too. And so once we simulated the OSIRIS data as well as new SABRE data, atomic oxygen data in that region, the model now does show the summer maximum in the upper mesospheric atomic oxygen, while at the same time still showing the winter light species bulge that is prominent in the thermosphere, which is a result of relative diffusion between heavy and light species. So we do have now a winter maximum in the thermosphere and the summer maximum in the mesosphere that's actually observed. And similarly for atomic hydrogen, we have now new data that from hydrogen data from data that now also show a prominent summer maximum. Summer maximum in the mid-latitude mesosphere, but then shifts back to a winter maximum in the thermosphere. Now, I'll point out in defense of the old model is there is really no atomic oxygen or hydrogen data in this region. It was actually remarkable that it did as well as it did to produce a peak there in approximately the right location. So, but with the new data, we were able to get a better result. Okay, another science highlight, and this gets to the climate change in the atmosphere. So here I'm showing on the left contour plots of the IMSIS zonal mean temperature as a function of altitude and latitude. And on the right panels, I'm showing the difference between IMSIS 2.0 and IMSIS E00. The top panels show annual average results, and the bottom panels show results for June solstice. Now, you can see that with the difference here, we have actually now cooler temperatures in the lower mesosphere and the stratosphere, and slightly warmer temperatures in the troposphere and the upper mesosphere. And this, in fact, is consistent with reported long-term trends, observed trends in the atmosphere over the time period between the data that went into IMSIS E00, which was from the 60s and 70s, and which went into IMSIS 2.0, which was post-2000. And this result is also qualitatively consistent with modeling results from WACMX. Here I'm showing the global average temperature change reported by Solomon et al. And this is the difference between 1974 and 2003, so similar time interval. And again, you see warming in the troposphere from increased CO2, but also cooling at higher altitudes, also from increased CO2. And primarily, there's other factors as well. Now, you don't see the increase in the upper mesospheric temperatures, and this is because the model results here reported in pressure coordinates. When you see, what happens is in altitude coordinates is that because the cooler temperatures in the middle atmosphere are contracting the whole atmosphere, you're actually pulling down the very steep temperature gradient into the thermosphere to lower altitudes, and that's why you get these observed apparent increases in temperature in the mesosphere. Okay, and the last science highlight I'd like to share is the implications of these temperature changes on densities in the thermosphere, and in particular molecular nitrogen. So excuse me, let me go back here. So on the left panel here, I'm showing the global average temperature profiles from IMSIS E00 in red and 2.0 in blue, and on this scale, they're virtually indistinguishable. But in the left panel, I'm showing the difference again, and you can see there's, in the middle and lower atmosphere, there's about roughly a 5 Kelvin difference. And this effective temperature is going to accumulate with altitude on the densities due to the hydrostatic effect that I talked about earlier. And so that by the time you get to the thermosphere, the modeled N2 density is now about 18% lower than it was in the old model. So this is a pretty profound change in density. Now, and it's also a very robust result because the N2 is very strongly coupled to temperature, especially in the lower thermosphere, as a result of being the dominant species down there. And because the temperature measurements that went into this are very self-consistent and robust. So we did in the model code, we do have an option to relax the nitrogen densities to the old model for legacy purposes, if necessary. However, that adjustment comes at the cost of very large hydrostatic imbalances in the model, which are illustrated in the right panel, which shows the ratio of the vertical pressure gradient to the mass density, and this is with respect to geopotential height. So when things are in hydrostatic balance, this value should equal the surface gravity of about 9.8 meters per second squared, but you can see when we make that correction to N2, it doesn't. So this really says that the thermosphere really has changed between the two models, and by implication also changed over the years fairly significantly. Okay, now so switching gears and going on to EMSIS 2.1, in which we added a nitric oxide component to the model. The motivation for doing this is that nitric oxide is one of the dominant cooling agents of the thermosphere that allows it to maintain thermal balance. And it's especially important during geomagnetic storms when it is enhanced and essentially acts as a thermostat. So that's the motivation for getting that in there. We also have a lot of good data sets we had to work with for that. And so that was one of our priorities, is to get that into the model. So here I'm summarizing the formulation that we used for nitric oxide. Above 122 kilometers, we use that same generic density profile that I showed earlier with the hydrostatic and ideal gas law terms that couple the density to temperature. Below 122 kilometers, we're using a cubic B-spline basis that's decoupled from temperature. However, in order to join these two segments together, we impose C1 continuity so that the weighting coefficients on the top two splines are actually determined by the temperature above. So the temperature influence actually extends down to about 110 kilometers. Now, I forgot to mention this earlier, but as with the other density components and with temperature itself, all these vertical parameters we selectively expand as a function of the other arguments of the model. So the horizontal location, the day of year, local time, and the solar and geomagnetic forcing. And then, but of course, also for the density, the temperature parameters themselves come into play here. So a lot goes into what comes out of the model in terms of density. Okay, and so here's a list of the data sets we used in the model. So several different techniques ranging from far infrared and some solar occultation to UV scattering to measure NO in the upper mesosphere and thermosphere. These data collectively cover about 30 years from 1991 to 2020. And for our fitting and analysis, we randomly selected 30 ensembles. The first 15 we used for fitting the data, and the second 15 we used for the validation and analysis. Now, the actual relative weighting of the different data sets was subjectively determined. We gave the most weight overall to the SNOWY data. This is a student nitric oxide experiment data, which has very good coverage from 100 to 150 kilometers. However, in around 100 kilometers, which is near where the NO density peaks, and all the data sets contribute roughly equally. Okay, so again, we always want to make sure that the model is fitting as we want it to. So here I'm showing, again, the residual bias of the different data sets as a function of altitude. And you can see the legend at the bottom right for the 6 different data sets, as well as the 7th, the Invasat schema that we used just for validation. And the top panel shows the average residuals as a function of altitude. with the left panel showing all data combined, and then going to equatorial equinox data, and then high latitude, mid to high latitude data during June solstice. So the latitude panels are winter and summer conditions. And so what you can see from, what you can gather from this is that the model is essentially representing the collective altitude dependence that the data is suggesting, at least to within the mutual biases that you see among the data sets. This is essentially, the best we can do overall until we can reconcile these discrepancies. You can also see that these mutual biases among the data sets amount to about a factor of 2 for the all data case, but it gets a little bit larger in the for when you look at more specific geophysical conditions. I should point out here that we always do these analyses in natural log space. So the values I'm showing here and in subsequent plots here, a difference of 0.1 here represents roughly a 10% difference, relative difference, and a value of 0.7 represents a factor of 2. Now, the bottom panels sort of put these average residuals in the context of the overall density profile. So these are the thick gray lines here are the model curves at the center of these bins that I'm showing that we use for the analysis. And what you can gather from this is that the data sets really characterize well the NO density profile. We have a well-defined peak, and also its seasonal latitudinal dependence. And so for example, one of the main features of the NO climatology is that the density peak is larger, broader, and lower in altitude during the high latitude and mid-latitude winter than it is during the summer. And all the data capture that, and as does the model. Okay, we also, of course, examined the variation as a function of other dependent variables. Here I'm showing the residual latitude dependence of both total and what we call partial residuals. So for total residuals, we subtract the model from the data with all the model variations turned on. So, and again, this is we want to see a flat residuals here to demonstrate that the model is capturing what the data are trying to tell us. Partial residuals, on the other hand, before we calculate the residuals, we turn all the model variations on except for the variation of interest, in this case, latitude. And then we also calculate a cut of the model through the center of the bin there as a function of that variable latitude. And what this allows us to see is sort of the shape and magnitude of the behavior of the data as a function of that variable, while at the same time filtering out the effects of other variables that might be different from data set to data set simply because of sampling. And again, we can see here that on the right panels that the model captures the data quite well. And in particular, at the lower altitudes, we see a winter maximum on the left. These are June solstice results again. A winter maximum on the left side of the panel in the winter hemisphere. At the lower altitudes, but the higher altitudes, this shifts 180 degrees, and at mid and high latitudes, you get a summer maximum as a result of the temperature coupling coming into play. And similarly, for looking at the day of year dependence of the model, again, the left panel, we're showing the residuals as a function of day of year, and you can see, and on the right panel here, I'm showing latitude day of year cross sections, 2 different altitudes, 100, 150 kilometers. And again, you can see that the annual variation of NO at mid to high latitudes goes from the variation shifts from a winter maximum at the lower altitudes to a summer maximum at the higher altitudes. And then turning to the solar activity dependence, one of the interesting things here is that the data sets don't have the same solar activity coverage, so it's really good to have overlap between data sets and use different data sets to cover the full range of solar activity. And you can see that in the model and in the data, there is basically a nonlinear dependence on the F10.7 index. And this is captured in the model formulation via the inclusion of quadratic terms in F10.7. And so at the equatorial latitudes shown here, you can see that the above 100, between 100 and 150 kilometers, the NO density increases by a factor of 2 to 3 from solar minimum to solar maximum, or actually from solar minimum to solar moderate. Above about 150 kilometers, it tends to saturate with this nonlinear effect. However, at low altitudes, and especially at high latitudes, there is some indication in the data and in the model itself that the solar activity dependence turns around again and starts going down at very high levels. This is an interesting, intriguing effect that we think warrants further investigation, and we hope to look at this at some time in the future. And then finally, with the looking now at the geomagnetic activity dependence, which of course is a major important feature of nitric oxide, is its enhancement during geomagnetic storms in the Aurora region. Again, we see, as expected, as a function of the daily KP index, the NO density increases, in this case by a factor of 2 to 4 from very quiet conditions to KP equals 4, daily KP equals 4 event. And then again, it saturates at very high levels. However, there is some indication, especially at the lower altitudes, that the NO density increases again for very strong storms. And this is not captured yet in the model, but it may be an indication of downward transport of NO during there's very strong storms. I will point out here too that this is just a fairly crude analysis as a function of the daily KP. The model also has a mode which depends on the time history, the 3-hour time history of the geomagnetic activity index, and that analysis might show a better representation during time evolution during storms. Okay, and then finally for MSIS 2.1, we compared with the previous state-of-the-art for empirical modeling of nitric oxide, which was Dan Marsh's nitric oxide empirical model, which was based entirely on snowy data. And again, snowy data was limited to altitudes between 100 and 150 kilometers. It also was limited to a single local time near about 1100. So here I'm on the left panels here, I'm showing cross-sections of the two models as a function of altitude and latitude. This is for quiet time June solstice conditions, and I'm showing the log density here. The right column shows the NOEM minus MSIS difference, so positive values or NOEM is bigger. The top row is for solar minimum conditions, and the bottom row is for solar max conditions. And you can see at solar minimum, the NOEM predictions are about a factor of 3 larger on average than MSIS 2.1. And this is a result of the fact that SNOWY's coverage as a function of solar activity did not extend down to solar minimum conditions. And so the NOEM model is essentially extrapolating down to there in a linear fashion, when in fact the nonlinearity actually drives the densities lower, which is captured now by MSIS 2.1. But at solar maximum, where there's the same data coverage in both models, we can see that they agree quite well in terms of their seasonal latitudinal dependence. And you can see the difference between the two models is now on the order of just 50% or so. One advantage that NOEM does have over MSIS is that it's constructed in magnetic latitude. And so it better captures the sharper auroral enhancements between 60 and 70 degrees geomagnetic latitude that we don't currently capture in MSIS. Okay, so to wrap up then for MSIS 2.0 and 2.1, so MSIS again represents the average observed behavior of temperature and now 9 species densities with the addition of NO. The most fundamental change from the previous versions is how we capture the transition of the atmosphere from the fully mixed region to the diffusively separated region. The model densities are now fully coupled to the entire temperature profile, so that variations at the lower atmosphere will project up to the densities in the temperature in the lower atmosphere changes will project up and affect densities all the way up to the top of the model. The MSIS 2.0 development focused primarily on altitudes below 100 kilometers using the extensive new data there. And this resulted in large improvements to the model temperature as well as to mesospheric O and H densities, especially with respect to their seasonal dependence. And the cooler stratospheric and mesospheric temperatures that resulted in the new model produce thermospheric N2 densities that are approximately 18% lower than IMSIS E00. And in the upper thermosphere, which we made some adjustments so that the O density is about 10% lower than the previous model as well. But otherwise, the IMSIS E00 thermosphere is largely retained. Now, in developing the model, one of the obstacles we faced was that the fact that this change in temperatures makes it difficult to reconcile old and new observations. And in particular, while there are several new data sets of temperature in the thermosphere, there really are very few to none observations of individual species densities recently. And so there's a disconnect with the earlier mass spectrometer data that was measured in the 70s and 80s. And so we concluded that in order to sort of make it further advances in climatological specification of the thermosphere, we're eventually going to need new mass spectrometer measurements of species densities in the thermosphere. But also new techniques for measuring temperature and species in the critical 100, 200 kilometer transition region. And of course, the GDC and dynamic missions would greatly help to address this issue. We also want to do work to reconcile these systematic biases that we see among both new and old temperature data sets, including accounting for long-term changes in the climate. And then just to quickly recap for the new nitric oxide component for IMSIS, it's based on observations from 6 space-based instruments, and the data sets are generally in good agreement. They have some height-dependent mutual biases up to a factor of 2, but in terms of their variation as a function of other variables, they tend to show very consistent results. This empirical representation is the broadest empirical representation of NO now available. It covers all altitudes from 73 kilometers to the exobase, all solar and geomagnetic activity conditions, and all local times. And we're continuing to try to improve and enhance the model. We're currently working on adding non-migrating tides as well as a new carbon dioxide component. And we're also working on comparing the new IMSIS NO model with the new recently released SABRE NO density product. Our next major task is to overhaul the IMSIS thermosphere, including some of the aspects that I just discussed. And we haven't really started it yet, pending available funding, but that is our next big goal for the model. We also want to add to the model uncertainty estimates to accompany the model output, so you can know, okay, what's the uncertainty of the climatological mean, and what's the uncertainty if you're using the model for day-to-day weather prediction. And the next 2 species we envision adding to the model would be ozone and water vapor. Now, we have a poster in tomorrow's session in which we sort of discuss these in more detail. So if you're interested in these aspects, I definitely invite you to stop by and take a look. And we love to have comments. We love to hear from the community about all aspects of the model. So if you have any comments or questions, please shoot us an email. And for any prospective postdocs in the audience who are interested in contributing, we do have an active NRC postdoc opportunity in the area of upper atmospheric climate. So finally, I'd like to circle back into my perspective of how empirical models contribute to basic science. You probably heard the aphorism by the statistician George Bell that all models are wrong, but some are useful, and perhaps this does apply to both empirical and physics-based models of the upper atmosphere. But I hope I've convinced you that IMSIS is not wrong most of the time, and that it is useful. Now, perhaps further evidence of its usefulness perhaps comes from how often the model is cited. And it turns out that it's quite often. In fact, IMSIS papers are the first, second, and fourth most cited in JGR space physics. Now, you might argue that a lot of these citations are papers that are pointing out that IMSIS is wrong. And that's perfectly fine. That's part of the purpose of the model. It's not just a benchmark. It's a target to shoot at and to make things better in the long run. But it's worth reflecting on what it actually means to say that an empirical model is wrong. You know, in the broadest sense, it says that the data underlying the model are wrong. But it could also mean that the data are incomplete, or that the model formulation is incomplete. And of course, for climatologies, they're not going to reproduce the weather of the day all the time, or any of the time maybe. So there's different ways that the model can be wrong, and it's important to keep that in mind. Now, IMSIS is only one of many very useful models used in geospace science and aeronomy, and there's a short list here. Some of these you might not sort of have considered as empirical models before, but they all, in fact, satisfy the definition that I offered earlier for an environmental empirical model. And these kind of models are used for many different applications in the science, and I'm listing some of them here. So first and foremost, they provide a distilled view of the historical observational record. And as such, they're a critical benchmark for assessing new measurements and first principles models. They're also very commonly used as boundary, initial, and background conditions for models that cannot otherwise calculate them from first principles. So their uses are wide and varied, and this is why they get cited a lot. So to conclude, then, I'd like to reiterate my assertion that the process of developing empirical models really is fundamental science. It leads to novel discoveries. And I'll give you just one example of that. The last example I have there, the IKEA 70 model of thermospheric density. So IKEA, in the process of developing its model, was trying to represent this very strong semiannual variation in thermospheric density to better represent, density for the satellite drag application. And he tried and failed to represent that variation in terms of a temperature effect alone. And so the implication was that atomic oxygen has its own independent seasonal variation. And this variation is something that first principles models to this day still struggle to capture. So it all starts with the data analysis and with sort of putting the data together into a coherent context. So I will get off my soapbox there, and thank you for again for the opportunity to share our results, and I'll be happy to take any questions. Okay.
Well, yeah, this is working. Thank you, John. That was truly spectacular. I think for members of the audience here who are maybe new to coming to these meetings or students, what you just witnessed was a masterclass in how to give a good science talk. Not just the science itself. John did a great job of showing how the model development can actually lead to physical insight. And I'm reminded of a comment that one of my colleagues made once. He said, giving a good science talk isn't easy, it just looks that way. And I think John made that look really easy, so thank you for that. I also wanted to comment, CEDAR is about connections, and you reminded me of a connection when you mentioned the astronomer Tycho Brahe. Tycho is an example of how not to follow the code of conduct that we have. He was a brawler and a philanderer, and he lost his nose in a sword fight duel with his cousin. And I love the fact that what they were dueling about was who was the better mathematician. So how's that for a historical note? He also had a pet elk that died by drinking too much beer and falling down the stairs. So don't be like Tycho Brahe, follow our code of conduct. But Thank you again, John. That really was a beautiful talk. We have time for a few questions. I think Lindsay is running Slido. Matt and someone will have the microphone, but we'll start with questions from the audience.
John, great talk, really interesting. I know Doug Robb at your institution is doing a lot of work with solar spectral irradiance. Are you guys trying to incorporate that into MSIS 2.2?
That is part of our goal for the thermospheric overhaul, is to use better proxies where possible for solar irradiance, and also to try to get away from the need for both the daily and the 81-day average, because what we found when we use things like the magnesium index is that 81-day average term really isn't necessary. It's really just a correction to the representation of EUV by F107. It's not so much a physical effect in the thermosphere.
Hi. So thank you so much for that extremely informative talk. The most mysterious part of MSIS for me has always been this anomalous oxygen, right? It has always been black magic. And my understanding, which you repeated at the beginning of this talk, is that it's actually not one thing. It's actually multiple different, it's hot neutral oxygen, but also O plus kind of mixed together. And that's really a problem for comparing to physics-based models, because in a physics-based model like, say, TiGCM, you're calculating O plus and you're calculating thermal neutral O, but there's no exospheric hot O, or, non-fluid, non-thermal. So can you comment on, first off, has the anomalous oxygen changed between EOO and 2.0? And also, do you have any idea how much of that anomalous O is actually O plus versus neutral, exospheric, non-thermal oxygen?
Yeah, that's a very good question. I will just make this comment. I had nothing to do with that parameterization. I wish Mike Piccone were here and Al Hadeen, because they were ones that. So it really was basically somewhat ad hoc way of accounting for discrepancies between the model and satellite drag data. And so the thought was, well, yes, there is this population of hot atomic oxygen that results from charge exchange with H+. But of course, oxygen ions can also contribute to satellite drag, so it's like, well, maybe it's also, the O plus ions as well contributing to it. So to answer your other question, what's in the MSIS 2.0 is basically transplanted from the other model. It has its own temperature. It's not coupled to the main temperature in MSIS. It's, I think it's even a constant temperature if I remember correctly, but it's its own population. It's a separate thing. We just basically transplanted without any changes. I would say for comparison, unless you're using satellite drag, unless you're doing satellite drag applications, you can probably just neglect it entirely in your comparisons.
I mean, but satellite drag is a huge part of the future of our fields. And getting satellite drag correct at, say, 550 kilometers is a huge part of the future.
Yes, absolutely.
Time for one more question. We have 2 Slido questions, and we should move on.
So this is, again, fabulous talk. Thank you so much. This is a non-technical question that I'm hoping will help a lot of students in the audience that maybe are not fluent in Fortran. Are there Python modules available for MSIS 2.0 and 2.1?
Okay, so being an old Fortran fogey, we don't have any intention to develop, I mean, we have a limited resource, obviously, to develop Python versions. Other people have done that, and we certainly are okay with that. I mean, we'd invite you to sort of collaborate with us first on that. But what we are planning on doing with the code enhancements, we're moving to more modern Fortran, Fortran 2008, which allows you to use ISO C binding so that you can actually plug your Fortran code into any other language, including Python. And so we're hoping in the future to provide support for that, put the wrappers in that people can use to call it from any language.
Cool. These next ones come from Slido, so anonymous people in the audience.
Okay.
The first one is, what would the ideal combination of measurements to what would be the ideal combination of measurements to improve MSIS? What atmospheric component would be the most important?
See, you asked me this, I'm going to say everything. I think, again, reiterating, where things are most uncertain is the lower and middle thermosphere, 100 to 200 kilometers, where even historically you have very little individual species data at the same place where you have this transition, this unknown transition from fully mixed to diffusely separated. We just really I think even the physics-based models don't have a good handle on that as well. We really need the observations to constrain that. And I think that would be my number one wish for new observations.
And the second one, I think this one has a quick answer. Why is there such a large difference in models depending on whether they report in geographic versus geomagnetic?
Okay, so for a lot of the variations we see, especially in temperature in the thermosphere, you have processes like the heating, and the auroral heating, of course, is more aligned to geomagnetic coordinates. And the NO production is more aligned in geomagnetic coordinates. So when you analyze things in geographic coordinates, you tend to kind of wash out that dependence. And so we are in the future, and we hope to sort of introduce additional parameter or variables in the data to sort of account for that and better resolve latitude dependence in both geographic and geomagnetic coordinates.
Mark, do we have time for one more?
If it's quick.
Okay, I will be quick. That's very nice to include the nitric oxide in the MSIS. I have a quick question. You showed the Kp dependence of a nitric oxide density at 100 kilometers and 150 kilometers. At 100 kilometers, the density enhancement during storm actually never go to the low latitude, but 150 kilometers go to the low latitude. Is it due to neutral wind difference at these two altitudes?
That's an excellent question. We haven't looked at that yet. I will. Yeah, the results I showed there for high latitudes.
Okay.
Yeah.
One comment. Actually, we derived nitric oxide current density from timed GUVI data using FUV spectral data, and we do see that sometimes even during moderate storm, we can see nitric oxide density current density can extend to the equator region.
Okay.
So this is still positive. That
Yeah.
is correlated well with the auto-entry depletion.
Oh, yeah, actually, thinking of it now, actually, at lower latitudes, at the higher altitudes, it is the temperature effect, because you do have sort of global heating due to the storms. It can actually influence, at a specific geometric altitude, it can actually enhance the anode, just due to the expansion effect.
Okay, well, thank you. We are eating a little bit into our break time now, so we should move on. So there's one last thing we need to do before the break, and that is, by tradition, we have a certificate to present to John for his, again, just fantastic talk that he's given us here today. And so we would like to present you with this certificate to recognise it. This really is quite a prestigious award to be able to present in front of the audience here, and thank you so much for such a good talk, John.
Thank you, Mark.
All right, thanks everybody. I think we now have a break. We should be coming back about 10, so there's coffee outside and we'll resume then. There'll be some information on rolling slide presentation during the break. Thank you.